Welcome all to this joint IMarEST RENA meeting. Dr. Stuart Cannon is research leader in really surface warship area and concentrating, I think, still on structural aspects. And his presentation this evening is talking on the role of welding technology in the performance of warships. And I gather it'll be construction, performance under sea loads, endurance, and so on. But I'll leave it to you, Stu, to fill in the details. So welcome, Stuart.
The outline of this presentation was firstly go back to the beginning of when welded structures were used for warships, and there's a particular example that I want to talk about. Then I'll go through some case studies of looking at the performance of welds and how they behave in surface ships. That's both to what I call the ordinary wave loading, and then I'll talk about some military loads. And as I go through the presentation, the idea was to disclose to the welding community what sort of R&D I need to take my profession into the future. So that's what we'll do here. So most people, when they were students and talk about welded ships, they all go back to the Liberty ships in 1943. What I wanted to do was go back a little bit further to 1936, when the UK naval programme decided they were going to build two mine hunters. That's the vessel on the far side there. They were going to build two ships in 1936, build them side by side, but the chief naval constructor of the day turned around and said, I want one of these ships to be built out of the conventional techniques, which is predominantly riveted with a few little welds in some of the bulkheads, but the second ship I want it to be built out of 100% welding. So it was the first time that two ships were built side by side using welding. The Leader was I think built slightly earlier, and the Seagull was the welded ship. You can see there the length, beam, draft, the displacement, and the speed that these things, these ships could do. The key factor that I want you to take from these principal dimensions is the length to beam ratio. Was about 7.1 for these two ships, and that's a number that I'll probably come back to a little bit later in the presentation. But just to give you an idea of these two ships, when you go back to the historical records and you look at them, you can see that they were laid down fairly close to each other. But the construction of the Leader, in other words the riveted ship, was 84 weeks, whereas the construction of the welded ship was 76 weeks. And there was 34 tonnes saving, about 10%. So as a naval architect, I get quite excited about that because I can put on more fuel, I can put on more weapons, I can extend the range, or have a lighter ship. So welding was starting to become a benefit to us as naval architects. When you look at the costing of those ship structures, you can see the skill sets that we used to build the ships down the left-hand side. Shipwrights went up a little bit. The riveters obviously lost out in this game. The drillers, again, to provide the holes for the riveters, were out of a job. But the welders were getting more work. And so you can see that in 1936 dollars, this actually saved $250 on the cost of the ship structure. So again, there were some benefits that we can use to spend that money elsewhere or have cheaper ships. Now I've got to go to my notes because again, these two ships were built side by side, and then they went out on sea trials side by side, and there were some interesting comments that were written by the chief constructor of the day about the ship. The sea trials, they went out, the wave heights were between 5 and 10 feet. The wavelength was between 60 and 80 feet. Maximum roll angle of about 25 degrees. Speed of 13 knots. And I'll read what the constructor said about these ships. He said, for both ships, the maximum stresses recorded were very low compared to the working strength of the material, and there were no appreciable vibrations occurred. Close examination of the structure of the Seagull revealed no weaknesses of connection, which was good for the welders, and the compartments below the waterline were in fact watertight. So that was a novel thing for a naval architect at the time. The ship is very free from creaks and groans and shows no appreciable signs of racking movements. So again, the technology seemed really good. The downside was that the constructor said the problem of distortion and its correction can now be said to be solvable. The real problem, which needs constant and careful attention, is the effect on work already completed in the ship due to welding, and the effect that this has on the other parts of the ship structure to be welded later. These effects are not apparent at first sight, but do occur a considerable time after the ship has been constructed. And the lightness of the construction will also enhance these effects. So the problems that we face in welded ship construction were there right on day one, and I still don't think we've solved all of them today. So that was interesting. But what's happened in the years to come, or the years later, these are the two, the current warship of the Australian fleet, the Anzac over there, and we've got the Hobart Air Warfare Destroyer on this side. You can see the length and beams of these ships. The length to beam ratios are similar for these two ships. They're about 7.9. And one of the factors on warship design is that when you've decided on your weapon systems, the propulsion systems, the ship structure, the crew, you can't actually change the mass distribution of the ship much. It's not like a bulk carrier or a tanker where you take on a lot of cargo and the mass distribution significantly changes. So you've got this beam of a certain length, certain width, certain depth. The mass distribution is fairly constant. What that really means is that the resonant frequency of these ships is about 2 Hertz. And that's fairly constant for all warships. There's not much you can do with it. And so when I've got a beam of that slenderness ratio in a seaway, and here's a picture of my ship, and this is explaining to welders rather than naval architects. I've got my waves coming down. They've got a wavelength of lambda travelling at a speed c, and the ship is moving across those waves at a certain speed v. It's in a certain heading angle, and it's the encounter frequency that I get that causes that ship to bend and flex in the seaway and cause a lot of the fatigue loading or the racking or distortion, if you like, that the initial naval architects considered. Because this was a bunch of welders, I really wanted them to see what a ship looked like in fairly benign sea states. So as an operator, I can change the speed of the ship, I can change the heading angle of the ship, and if I hit one of these resonant frequencies, then I'm going to excite the bending moments on the ship, and this will cause fatigue on the ship structure. There's been a lot of work on the sort of hydroelastic response of ship structures over the years, and this is just one of the types of results that I was interested in talking to welders about. These plots are the shear force and bending moments at each section along the ship's hull, and you notice towards the bow the scales are different so that they align on top of each other. You see the shear force and bending moment diagrams are actually in phase with each other, whereas towards the aft of the ship, the phase of that shear force and bending moment diagrams are separate. What that really means is towards the bow of the ship, I'm getting principal stresses that are alternating in one direction. So if I've got a weld that's perpendicular to that, is that more damaging than a weld that's parallel to that? And this is an issue that I don't believe has been resolved today. Whereas towards the stern of the ship, the principal stresses are rotating. So that's a very different load pattern that's being applied to the ship structure, and we don't understand that at the moment. Fatigue still occurs, and I wanted to talk about some examples, so I was going to talk about the fatigue of the Anzac bilge keels. So that wave loading causes the ship to hog and sag as it goes through the waves. There's lots of structural damping, and there's water dampening, which means it doesn't resonate and fall into two bits and sink. But those wave loads cause global fatigue loads. The bilge keels on the Anzac class here are a plated structure. They're about 300 mil wide, about a metre long, plated structure that's welded onto the side of the Anzac ships by a couple of double plates here. And the newspapers told us that the bilge keels were cracking due to fatigue after about a year of service. And the issue was, why is this? You can see here some of the cracks were occurring at the welds between the double plate and the hull plate, and again between the upper surface of the bilge keel and the double plate. Just inboard of this are some fuel oil tanks, and so the fuel oil worked its way out, ran up to the surface, produced nice pretty colours. So you've got a perfect NDI technique to work out whether it's cracking or not. Anyway, was I worried about this? I was, because as a young graduate naval architect, when I was working for a consultancy, this was my first job, where the Kurdistan had completely split in two due to a weld defect in the bilge keel, and I wasn't looking forward to explaining a similar circumstance with an Australian warship, so I wanted to do something about it. One of the issues that we were concerned about was the hydrodynamic loads on the bilge keels, and there wasn't too much data about what those loads are. So we looked at the seakeeping codes, and when you've got a seakeeping code, you put a bilge keel on and you predict the amount of roll damping. That roll damping moment must be equivalent to the structural loads. So we attacked our seakeeping codes so that we could predict the loads on the bilge keel due to the rolling of the ship. We did that for each of the sea states that we're likely to experience. We loaded the FEA models and did some spectral fatigue analysis for each of those sea states. And then we looked at the long-term operational profile of the ship to work out whether a redesign of the bilge keel that was done by Tenix here in Williamstown was going to be useful or not. So that was all analytical and theoretical, but you've got to do some experiments to confirm that your loads are reasonable. So whilst they were replacing the bilge keels over in the west, we strain gauged the inside of the bilge keels with some wires that went through the hull, and then we asked the welders to weld the bilge keels back on without damaging the strain gauges. They did that. It was quite successful. Whilst the ship was in dry dock, then we could hang heavy weights on the side of the bilge keels, calibrate the FEA model to validate our long-term predictions. And so you can see here that although the loads were fairly small, the comparison between the experiments and the finite element analysis was pretty good. So we were quite happy with our FEA model representing the real ship. Then the ship went out and did a sea trial, which basically means it travels at various speeds in various heading angles, and we measure the response for each sea state. We compared the measured response with the predicted responses, and again we got a fairly good correlation. One of the issues with putting monitoring systems on board a ship is they never see extreme waves ever again. So the sea states here were fairly small. So we left that monitoring equipment on board the ship for a couple of years to collect more data and hopefully experience some larger sea states. Whilst this was going on, the rules, because it was a rules issue, the GL rules at the time increased the pressure on the bilge keels for the fatigue calculations up to 85.5 kilopascals. Our predictions said that over the life of the ship, the expected loads we should have was about 82. This compares with 16 that was in the original rules at the beginning of the day, so they're out by quite a lot. So we were happy with this. The only problem now is that I've got the global bending of the ship causing the stresses in the longitudinal direction, that the bilge keels experience, but I've also got the roll damping loads that the bilge keels will experience. And so I've got another multi-axial fatigue problem, and I don't understand how I bring that into the fatigue life calculations for ship structures. The good thing about the bilge keels is that they were modified, and modified design went on. The modifications were designed for the loads that we came up with. But the critical failure locations now have changed from the outside of the bilge keel to a position that's way inside of the bilge keel. But now I've got no way of telling whether they're cracking or not. So what NDI techniques can I use? Is there any coating I can put on the welds at the beginning of the day to give me an indication that through the life of the ship I'm experiencing some failure there? The good news is those bilge keels are on the ships. We've had no problems from them since. So that was another good outcome. I've talked about the wave loading and the roll damping loading, but ships also slam in various sea states. You can see the pictures of the Armidale class patrol boats there, but again, going back to the FFG, a relatively benign sea state, but the pitching motion of the bow is quite excessive, and we're getting quite large slams occurring. The little bit of string there is because they're doing a replenishment at sea activity, which is why we can film the ship from this side. So the problem I've got now is each time the bow emerges, hits the water, we get a slam load, and that slam load can excite the resonant frequencies of the ship as well. So I believe this, to investigate this, we've put a monitoring system on one of the Armidale class patrol boats, and there's a number of strain gauges located all around the ship. You can see from the traces over here, these are the stresses on the strain gauge, and you can see here that where the ship's changed heading angle and dropped to speed, the response of the ship has dropped significantly, so that will save some of the fatigue life. So now you might even have to bring in the mindset of the ship driver, the commanding officer, into the fatigue life calculations. How does he behave in certain sea states? And that's something that we need to understand. So we've collected some of the data on the Armidale class patrol boats and obtained the frequency responses. You can see here the first distortional mode shape and the second distortional mode shape. For my mechanical engineers in the audience, that's not wave loading. That's probably the engine cyclic frequency that's causing that bit of fatigue, but I'm only worried about the sea states here. So we can separate the wave loading, we can separate the slam whipping responses and look at the impact that that has on the fatigue life. And certainly for the Armidale class patrol boats, if they're doing a lot of slamming, this can increase the or reduce the fatigue life by about 30 to 60% compared to the ordinary wave loading. So again, miner's rule is great, but the question is, what happens if I do this at the beginning of the life of the ship and not at the end of the life of the ship? What's the order of events? So what's the operational profile of the ship, and how does that impact the fatigue life? And again, there's no rules in the Eurocode 9 for bringing in the order of loading, and it's quite important for the fatigue life of ship structures. And you can see here within the engine room compartment a couple of the fatigue cracks that are occurring because of that loading. So they're the seaway loads where you excite these resonant frequencies, but there's other loads that we deal with in warships that excite these frequencies as well. So the first thing I wanted to convince my audience is that this old image of a torpedo whizzing along the surface and impacting the side of a ship is something that's in history. A modern torpedo, as it leaves the ship or the submarine, goes down to its operating depth. On the case of the submarine, flies by wire, eventually finds its magnetic signature of the ship, and then it decides to blow up. It's the response to the explosion underwater that is that excites these loads again. So this slide was put together to assist the Koreans when we're assisting them in the sinking of the Chinoan. So what happens is the torpedo heads towards the ship, it finds its signature, it explodes. That explosion underwater at a fairly deep depth causes a bubble to grow. It grows very rapidly, such that it overstays its equilibrium, so it gets bigger than what it should be. And then the hydrostatic pressure says, hang on a minute, I've got to squash this back again. So it squashes it back again, and it does it too quick again, so it goes much smaller. So this bubble resonates underwater. That resonating of the bubble causes a pressure pulse to go up through the sea, and that's what's going to cause the excitement of the ship to break. Ultimately, the bubble will hit the surface and it will plume through the ship and rip the top of the ship off. That's a very hard, impossible design case to withstand, so the limit state here is certainly nowhere near that event, but it does occur. This is the Chinoan that was torpedoed by the North Koreans a number of years ago now. I can't remember when it was. The two pieces of the ship obviously sank and they were recovered, and you can see the computer modelling that was done to see where that water plume goes through. I'm not suggesting we design against this, but that's the end state. So what happens when we do undex trials on ships to test this? We tend to bring the explosion away from the ship so the water plume misses the ship, and we measure the resonance, we measure the hogging and sagging of the ship under these loads. For a certain size of undex, generally it's about 50% is the initial shock wave, but 50% is the bubble loading afterwards, and then the second bubble is a smaller percentage. So that's going on underwater. Here is our underwater test facility but this is just north of Melbourne, underwater, high-speed camera. There's an explosive charge in there, and it'll set off, and you'll see the bubble grow and shrink as if it was a torpedo load. So that's the initial expansion. Then the hydrostatic pressure's squashing it back again. And then all of a sudden it starts to expand again. It's upside down, so it progresses to the ship. The far side is Torrens, I think it was Torrens. A torpedo from Collins was fired at Torrens, and again you'll see this was in the press, saying that there were two loads in there. There weren't two loads, it's the water plume coming up afterwards. But you'll see the torpedo explode, you'll see the ship start to whip, and then the water plume will come through the ship and the welded top of the superstructure will come off. Again, we can't design for that, but it gives you an idea of what the loads we're interested in. So when we're defending warships in a survivability sense, we have like a layered approach. The first thing you want to do is you don't want to be seen. If you are seen, you don't want to be hit. And if you are hit, then can you survive? So if we can improve the strength of the ship to that whipping, that means we can take a hit of a weapon slightly closer. That gives us more time for the warfighters to defend against. So the ultimate strength is important. So ultimate strength is just like a tensile test on a ship, except that we bend it progressively and we measure the moment. It goes through an elastic response, which is what we're designing against. Then there's an elastic plastic response, and then it goes into claps where you get buckling and all sorts of behaviour on the ship structure. And it occurs both in the hogging condition and the sagging condition. Joe and Paik in Korea looked at aluminium ship structures and looked at the types of welding deflections that he's likely to see in ship structures. And he identified these 5 types of deflection. First of all, the plate deflection caused by welding, stiffener deflection where the stiffener is shifted slightly, the breadth of the heat affected zone in aluminium structures, residual stress in the plate between welds, and residual stresses in I-beams on ship structures. So again, staff at work took these results and applied them to the Armidale class patrol boat. The Armidale class patrol boat's made out of aluminium, 5083 for the plating and 6082 for beams and stiffeners. So we applied those deflections, those welding issues, onto the ultimate strength of this ship to see what was important. And again here you can see for the plate deflection, the black line is the perfect ship structure. And again, Joe and Pake looked at slight imperfections, severe imperfections and an average imperfection, and he looked at all imperfections together. So you can see here for plate deflection of both the stiffener and the plate, there's a significant drop in the ultimate strength of the ship's structure by having those deflections. So if our welders give us lots of deflections, etc., it reduces the strength of our ship, which again impacts the ultimate strength, which impacts the distance that we can have for weapons, effects, etc. Again here you can see the heat affected zone breadths again. It's caused a reduction in the ultimate strength of the ship structure. So again, large heat affected zones have an impact on the ultimate strength, which has an impact on the overall integrity of the ship. And again here you can see the impact of the residual stresses on the ultimate strength. So again, predicting the ultimate strength is very important, but then if I go to damage strength once a weapon's hit, the impact of the residual stresses, the impact of the weld distortions, etc., impact the strength of the ship and impact the damage control that could have had. So again, very important that we have a good understanding of that. Going back to the work on the Seagull, where he said that the welding in one part of the ship affected another part of the ship, that means that the distribution of those deflections, the distribution of those residual stresses will be different around the ship. That modelling that we did, we assumed the same deflections over the whole ship. So there's a challenge there for people to understand how does it vary across the cross-section of a ship. So it's quite pleasing for me when the white paper came out and the defence industry policy statement. There was an example of some work done by the DMTC that was looking at pulsed tandem gas metal arc welding, and the driver for that was to reduce residual stresses and distortions in welded steel structures. And one of the builders for the AWD used that technique and came up with very low distortion welds for the air warfare destroyer. And you can see the picture of the UK ship there, the old Hungry Horse effect, where the plates are distorted between the stiffeners, has quite an impact on the strength of that ship. So it's good that we're using such techniques. They were, that's underwater, where we're looking at the resonant frequency of the ship again. There's other loads that warships come up against, and that's things like air blast. So this is an old DSTO experiment of the day where we took an old warship and applied surface weapon hits to it. If you want to know what it's like in a ship with weapons loads, then I recommended to these guys that they read this book, 4 Weeks in May, which was the story of Coventry. So that was during the Falklands War. It's his biography, and he describes life on board the ship. He describes going down to the Falklands and being the target ship, and he describes all the exocets hitting the ship and the evacuation of the ship and who survived and who didn't. Very, very sad book, but it shows you what's going on. So we've got here a ship where we're going to hit it with a weapon in that area there. You'll see the weapon go off, and then we'll go inside the ship and look at the consequences of it. And the primary reason for showing this is the longitudinal bulkheads and the type of failure that occurs from this hit. So that's where the weapon hit. Then we go inside. The weapon hasn't hit yet. There's all the fixtures and fittings and everything that fly all over the place, but see what type of damage it's done. But you can see the bulkheads there have bowed. So they're connected up at the deck head and they're connected at the deck. They've bowed out because of the air blast pressure. If you get too much bowing, too much distortion, then you're actually going to block that evacuation route. So you actually want that bulkhead after that event to be fairly straight still so that you can evacuate out. And so again, DSTO, we looked at different welded connections between different bulkheads. So you can see there's 3 types of welded connection for a bulkhead into the side of the ship. We take those bulkhead designs, we chuck them in a hole in the ground, certain charge size, certain standoff distance, and blow it up. And you can see the 2 different end connections give very different responses to the same structure, the same steel. That's very good for a design right at the beginning of the day, but what happens as the welded structure ages? So it's got lots of fatigue cracks in it, it's got lots of corrosion around the welds area. How does it perform 10 years after it's been built, 15 years, 20 years, etc.? And that's a current challenge. We know that the larger the ship, the longer we keep it. And the ship lives are becoming longer and longer. The American carriers there are over 40 years. And as you can see, the smaller the ship as we go down the page, we tend to keep them longer. Australia's probably got its largest ships that it's ever had. So does that mean we're going to keep them much longer than what we think we're going to keep them for? So we need to understand the ageing problem. And we're not very good at that. If any of you read the Rizzo report, the corrosion and fatigue cracks in the LPAs, etc., was not a very pleasant story. So we're starting to look at the structural models, find out what data do you need in terms of the corrosion along the welds, what data do you need in terms of the cracks. Are you looking at multiple fatigue crack scenarios rather than a single crack in a ship? It's the old toilet paper syndrome. Is that worse than a single crack? So we're looking at the FEA models, trying to work out what we need to predict the life of aged ship structures against these types of loads. Again, that's steel, aluminium. Again, another very good Australian success story, the CEA radar system, so the phased array radar system that's gone on the ship here. It was modified by Tenix. Very good radar, needs to be up high, a lot of weight upstairs compared to the unmodified ship. So the only solution there is welded aluminium structures again, and a very good design was put together for this ship, which has certainly enhanced its capabilities. The cupola holding that phased array radar again is built out of 5083 plates and 6082 extrusions for its lightweightness. And again, how do these respond to some of the air blast loads? But also when it's under air blast, will that structure remain intact? Will the welds rotate and fail? And secondly, if a modern weapon system's got fragments in it and those fragments are a shape charge, so they fire a certain direction, how does that load impact the strength of the welded structure? So we've got aluminium boxes here with welds on each of the corners, and we've got an air blast in the middle that blasts, and we've got fragments that charge off and load this type of structure. And then we're trying to model it with different techniques. So you can see here the air blast has gone off. You can see the distortion in the plates, but the integrity of the welds are fairly good in this one. And again, where the fragments have hit them, they haven't been enough to initiate a zipping effect. And again, using an IMarEST system to predict the stresses, or the strains in this case, on that system while it's being exploded. It's fairly good. Fire is another problem in aluminium structures again, and the behaviour of weldments during fires. There was a lot of fire on ships in the Falklands, etc., but we have smaller fires, and so how good are they for welded structures? So these two graphs show the show hardness up the side and maximum exposure temperature along the bottom. So 0 degrees here up to 500 degrees. And the different colours are exposure to various temperatures. So as we end up with a high, in this 5083, you can see we're getting a 20% reduction if we have a fire between 300 and 500 degrees for even 15 minutes, up to 240 minutes. And again, with the 6082, there's a much larger drop in the hardness values over those temperature ranges. And if hardness is related to strength, and we have a fire of one of these magnitudes, then the strength of the ship structure is going to change. This is just the welded sample for the 6083, I think. And again, the middle of the weld is here. The heat affected zone comes out here. You can see for the baseline, the hardness runs up here. And as we increase the temperature of the fire, the hardness drops quite a bit. But on this particular material, because of the alloying, as we continue to heat it, it actually recovers again as well. What happens if we have a fire of that magnitude on a ship? You can see in this next graph I've got two welds, one where I've got the 6082 material and one where I've got the plate material, and the second is the extruded material. For the same fire, the strength of that weld has changed depending on what material it is. So if I have a fire on a ship of a small magnitude, I'm changing the structural integrity of that ship. How big a fire? Not quite sure yet at the moment. This picture is the Bundaberg that was from Channel 7 News, a very excessive fire. But we have fires on washing machines on ships. That's enough to change the strength of welded joints on the Armidale class patrol boats. And I need to understand that as my ships are getting older and older. So that's really what I talked about. This was just a video of a montage video that people put together so that people could remember what was going on. There is some music, but my speakers are quiet. So I put this up while you think of questions. Yeah?
Examined any friction stir welding or adhesive bonding?
Of aluminium,
Yep.
there was some work done a number of years ago. Certainly the New Zealanders did a lot of work because the aluminium superstructure on their inshore patrol boats was all stir friction welded. But I haven't done any work in that. And there's certainly some work now going on in steel, in stir friction welding, etc. There was a number of papers at this conference.
Okay, yeah. Because the experience I've had with friction stir welding has much less
less distortion, less residual stresses, so it's got to be good.
Yeah.
But I don't think it's at the place where we'd use it in a shipyard to its full extent.
What about bonding? You haven't looked at bonding at all?
Bonding, we haven't done any work on adhesive bonding, as far as I'm aware. But we did, certainly in the UK a number of years ago, there was a lot of work on adhesive bonding of steel structures. But again, it's the NDI. How do you guarantee that you've got a good bond in adhesive bonding?
Well, no, there's some new adhesives that bond aluminium without any preparation.
Yeah.
And they get very high.
Yeah, I haven't looked at any personally. Yeah.
Stuart, referring back to the Torrens video, and I always get quite distressed when I see that because my cabin was right above.
Right.
How
Sorry.
localised is that?
Sorry?
So from the point of view of watertight bulkheads, forward
Yeah.
and aft of that, and the the potential to save life
Yeah.
and escape from
Yeah.
the two halves,
Yeah.
how localised is that effect?
Yeah, it's always been very difficult to predict. However, what I would recommend to you, if you're interested in that, is if you go to the technical report that was the technical report that was produced after the Chinoan incident, the South Korean ship. That investigation was led by the Swedish, because apparently they're the arbitrators between North and South Korea. And then there was a team from the UK, America and Australia that were involved in analysing that particular failure. The report was incredibly detailed. The thing that got me about the report when we were working on it was half the crew survived, half died. And all of the witness reports of the crew that were on board the ship have been published. And they say where they were when the event took off, and it gives you an idea of what the range of the plume going through the ship must have been. They'll survive the whipping, they'll survive the structural loads that we design against, but that plume going through, you'll never design against it. And it was, it's a fascinating, it's freely available on the internet. If you can't find it, email me and I can squirt you a copy. But it probably a third of the ship was, they were gone. The bow and the stern was survivable.
Stu, has it come to a halt now?
Yep. All I put up at the end there was thank you for listening, and the fact that welding was key to the structural integrity of ships and helps save sailors' lives at sea, which is what we're up to. So you can MC John to your heart's content.
Yes. Thank you. Since I retired 14 years ago now, there's some brilliant work melding materials engineering and structural work and all the service and military loadings, and some of the progress presented in understandable terms. That's really wonderful, and it's heartening that people continue after I retired. And also, I had to get that in, also the fact that materials engineering is coming back to the fore. It's a personal thank you. Have we time for further questions?
So in the absence of any further questions, I'd just like to thank Stuart on behalf of IMarEST and Rainer for a very informative presentation. It was really good, Stuart.
Thank you very much. Thank you for inviting me.